All right. Tonight on Nights. Tonight on Nights. Uh, that's not mine. You guys know what that's from? Drop a comment. Oh, we got a cat. I don't know, a Bronco. Heading eastbound. I think that's what it says, or something like that. It's like, oh, we found this on him. Smells be catnip. That's not mine. Probably sound like a crazy person talking to myself right now. If anyone knows what I'm talking about, you're a real one. All right, let's get into the meat here. Pause. All righty. Hope you're having a good day today. Welcome everybody. Welcome one, welcome all. Welcome one, welcome all. Today marks a good special day. I actually, I'm gonna wait for some people to get in here before I start because I want to make sure the audio is good because I was looking back to some of my previous readings. The audio is a little quiet, so I want to make sure that it is, um, satisfactory. So let's wait for a couple of homies to get in here. Reading, um, C programming, a modern approach, chapter 3, live now. Dun dun dun. Okay. Let's let some people roll in here. Let's get the Twitch rolling. Let's play some tunes while we wait. All right. Okay, let's just go ahead and get started here without further ado. Ado. Welcome one, welcome all. It's time to program. Wake up. Time to learn some programming. So some people roll in here. Oh, we got a couple in here. Yo, hello everybody. If you're here, let's hear a chat. Make yourself known. All right, let's go ahead and I want to make sure if you're here, could you please let me know how the mic is? If I could turn it up, turn your volume all the way up on YouTube and on your device, and let me know if the audio is really loud or if it's really quiet, or compare relative to how it should be on your device. I am trying to make sure that it's good for the audio and reading. I don't want it to be too quiet. I want to make sure that it's you guys can at least hear it on the recording back. Oh my gosh, my hair is crazy. Oh boy. That's even worse. Okay, I'll be right back. Alright, that's fine. That'll do. Let's give the kitty and the puppy a little scratch on the back and scratch on the head. There you go. Alright. Cool, we back. Okay, let's go ahead and just jump on into the stream. Without further ado, let's not waste any time. Let's just get going here. We don't we need anybody, we just need ourselves. Here we go. Let me start the recording and we'll get going here. All right. Hello, everybody. My name is Michael and welcome back. Thank you much. Oh, gosh. Here we go. All right, hello everybody. My name is Michael, and thank you so much for joining me, and welcome back. We are going to be jumping back into C Programming, a Modern Approach by K.N. King. This is the second edition. Today we're going to be jumping, let's just get there first. No, not that far. Not that far. Here we go. Today we're going to be jumping back in. Today we're going to be reading Chapter 3, Formatted Input Output, and I hope you enjoy. This is a condensed version of my live stream where we go over the notes and practice problems. If you'd like to gain the full experience, please join me for the live stream. Thank you so much. Let's get started. All right, that'll do. All right, jeez. All right, I'll make a little thing here. Actually, I'll say. My personal notes on the chapter can be found on my GitHub, linked in the description below. Let's go ahead and get started. All right, cool. Here we go, boys. Welcome in, welcome in. We should be able to finish the full chapter today. It's not that long. Should take us less than an hour, I think. Chapter 3, Formatted Input Output. In seeking the unattainable, simplicity only gets in the way. Scanf and printf, which support formatted reading and writing, are two of the most frequently used functions in C. As this chapter shows, both are powerful but tricky to use properly. Section 3.1 describes printf and Section 3.2 covers scanf. Neither section gives complete details, which will have to wait until Chapter 22. Neither section gives complete details, which will have to wait until Chapter 22. 3.1. The printf function. 3.1. The printf function. The printf function is designed to display the contents of a string known as the format string. With values possibly inserted at specific points in the string. When it's called, printf must be supplied with the format string, followed by any values that are to be inserted into the string during printing. Printf string, expression1, expression2, ... The values displayed can be constants, variables, or more complicated expressions. There's no limit on the number of values that can be printed by a single call of printf. The format string may contain both ordinary characters and conversion specifications, which begin with the %character. A conversion specification is a placeholder representing a value to be filled in during printing. The information that follows the %character specifies how the value is converted from its internal form binary to printed form characters. That's where the term conversion specification comes from. For example, the conversion specification %d specifies that printf is to convert an int value from binary to a string of decimal digits, while %f does the same for a float value. Ordinary characters in a format string are printed exactly as they appear in the string. Conversion specifications are replaced by the values to be printed. Consider the following example. Int I and j are declared. Float x and y are declared. I equals to 10, j equals to 20, x equals to 43.2892, f, y is equal to 5527.0f. Printf, I is equal to %d, j is equal to %d, x is equal to %f, and y is equal to %f, \n, I, j, x, y. The call to printf produces the following output. The ordinary characters in the format string are simply copied to the output line. The four conversion specifications are replaced by the values of the variables I, j, x, and y in that order. C compilers aren't required to check that the number of conversion specifications in a format string matches the number of output items. The following call of printf has more conversion specifications than values to be printed. Printf, quote, %d, %d, \n, and with just I. Printf will print the value of I correctly, then print a second meaningless integer value. A call with too few conversion specifications has similar problems, where printf to %d, I, and j. In this case, printf prints the value of I but doesn't show the value of j. Furthermore, compilers aren't required to check that a conversion specification is appropriate for the type of item being printed. If the programmer uses an incorrect specification, the program will simply produce meaningless output. Consider the following call to printf in which int variable I and the float variable x are in the wrong order, where %f is here and %d is here, I and x. Since printf must obey the format string, it will since printf must obey the format string, it will dutifully display a float value followed by an int value. Unfortunately, both will be meaningless. Conversion specifications. Conversion specifications give the programmer a great deal of control over the appearance of output. On the other hand, they can be complicated and hard to read. In fact, describing conversion specifications in complete detail is too arduous a task to tackle this early in the book. Instead, we'll just take a brief look at some of their more important capabilities. In Chapter 2, we saw that a conversion specification can include formatting information. In particular, we use the %.1f to display a float value with one digit after the decimal point. More generally, a conversion specification can have the form of %m.px or %-m.px, where m and p are integer constants and x is a letter. Both m and p are optional. If p is omitted, the period that separates m and p is also dropped. In the conversion specification, %10.2f, m is the 10, p is the 2, and x is f. In the specification %10f, m is 10 and p, along with the period, is missing. But in the specification %.2f, p is 2 and m is missing. The minimum field width m specifies the the minimum field width m specifies the minimum number of characters to print. If the value to be printed requires fewer than m characters, the value is right justified within the field. In other words, extra spaces precede the value. For example, the specification of %4d would display the number 123 as .123. In this chapter, I'll use the dot to represent the space character. If the value to be printed requires more than m characters, the field width automatically expands to the necessary size. Thus, the specification %4d would display the number 1, 2, 3, 4, 5. As 1, 2, 3, 4, 5, no digits are lost. Putting a minus sign in front of m causes left justification. The specification %-4d would display 1, 2, 3 as 1, 2, 3 space. The meaning of the precision, p, isn't as easily described since it describes the choice of x, the conversion specifier. X indicates which conversion should be applied to the value before it's printed. The most common conversion specifiers for numbers are d, displays an integer in decimal base 10 form, p indicates the minimum number of digits to display, extra zeros are added to the beginning of the number if necessary. If p is omitted, it is assumed to have the value of 1. In other words, %d is the same as %.1d. E displays a floating point number in exponential format, scientific notation. P indicates how many digits should appear after the decimal point. The default is 6. If P is 0, the decimal point is not displayed. F displays a floating point number in fixed decimal format without an exponent P. F displays a floating point number in fixed decimal format without an exponent. P has the same meaning as for the E specifier. G displays a floating point number in either exponential format or fixed decimal format, depending on the number's size. P indicates the maximum number of significant digits, not digits after the decimal point, to be displayed. Unlike the F conversion, the G conversion won't show trailing zeros. Furthermore, if the value to be printed has no digits after the decimal point, G doesn't display the decimal point. The G specifier is especially useful for displaying numbers whose size can't be predicted when the program is written, or that tend to vary widely in size. When used to print a moderately large or moderately small number, the G specifier uses fixed decimal format, but when used to print a very large or very small number, the G specifier switches to exponential format so that the number will require fewer characters. There are many other specifiers besides %D, E, F, and G. I'll gradually introduce many of them in subsequent chapters. For the full list and for a complete explanation of the other capabilities of conversion specifiers, consult section 22.3. Program. Using printf to format numbers. The following program illustrates the use of printf to print integers and floating point numbers in various formats. Prints int and float values in various formats. So we include the standard I/O. We have int main void. Our main function returns an integer and has no parameters. We declare an int I and a float x. I is equal to 40 and x is equal to 839.21. We call printf %d, %5d, %-5d, %5.3d onto the I integer. We call %10.3f, 10.3e, and -10g to the x float value, and we return. The bar characters in the printf format strings are there merely to help show how much space each character occupies. The bar characters in the printf format strings are there merely to show how much space each number occupies when printed. Unlike % or \, the bar character has no special significance to printf. The output of this program is 40 with this one. So just by printing out the number by itself, prints out the number 40, %d. %5d adds what it said, right justification, or right, what did it say earlier? Yeah, right justified within the field. So this shifts all the characters to the right. Think of like the characters within their own single cells of their print call areas, right? So this would shift the characters to the right that you're printing within this %d and add 5 characters in total. So basically you're creating a limit to the amount of characters that are being printed within this %d justification. Or what is it called? Conversion specifier, rather. So this number specifies the amount of total digits to be printed within this call to this specific conversion specifier for your value of that variable. So for the specific print of this conversion specifier, we're going to have 5 character spaces. And with it being a +5, we're going to right justify all the characters that are in our actual variable within these 5 characters available. So it's going to shift the 4 and the 0 all the way to the right side of the characters available, thus having, you know, 3 preceding blank space characters. Same is kind of true for this negative, but it is left justified, where we shift the characters to be printed within the conversion specifier to the left of the 5 total characters available within this print for this specific chunk, or like insertion, right? And so it would look something like this. Now with this one, we have 5 characters, right, in total to be printed, and we have a decimal here, which is 3 characters total. Or these significant figures, basically, right? So because we can't add 40 to the end of this print, because that would make it 400, and we can't add a decimal point 0 to the end of this print because that would make it a float. It adds a 0 before it to still be 40, but now you just have 3 figures printed and formatted for this specific conversion out of the 5 right justified character spaces. Now for this other example, we have 10 possible character spaces, and we have 3 figures after the float, right? And it's positive, so it's right justified. Whereas here, we display an exponential format. And then this negative 10 makes 10 possible character spaces, but left justified, and the G displays a floating point number in either exponential format or fixed decimal format, depending on the number size. So it fluctuates. So this number was small enough to actually print out the number itself rather than the exponential form. Let's take a closer look at the conversion specifications used in this program. %d displays I in decimal form using a minimum amount of space. %5d displays I in decimal form using a minimum of 5 characters. Since I requires only 2 characters, 3 spaces were added. %5 negative d, right, or negative negative 5d displays I in decimal form using a minimum of 5 characters. Since the value of I doesn't require 5 characters, the spaces are added afterward. That is, I is left justified in a field of length 5. %5.3d is displays I in decimal form using a minimum of 5 characters overall and a minimum of 3 digits. Since I is only 2 digits long, an extra 0 was added to guarantee 3 digits. The resulting number is only 3 characters long, so 2 spaces were added for a total of 5 characters. I is right justified because the 5 characters is positive. %10.3f displays x in a fixed decimal form using 10 characters overall, the 3 digits after the decimal point. Since x requires only 7 characters, 3 before the decimal point and 3 after, and only 1 for the decimal point itself, 3 spaces were precede x. 10.3e displays x in exponential form using 10 characters overall, with 3 digits after the decimal point. X requires 9 characters altogether, including the exponential, so 1 space precedes x. And the negative 10g displays x in either fixed decimal form or an exponential form using 10 characters overall. In this case, the printf chooses to display x in fixed decimal form. The presence of minus sign forces less the presence of the minus sign forces less oh my gosh. The presence of the minus sign forces left justification, so x is followed by 4 spaces. Exactly what we were able to deduce out on our own. Perfect. Okay. Escape sequences. The \n code that we often use in format strings is called an escape sequence. Escape sequences enable strings to contain characters that would otherwise cause problems for the compiler, including non-printing control characters and characters that have a special meaning to the compiler, such as quote. We'll provide a complete list of the escape sequences later. For now, here's a sample. \A is alert or bell, \B is backspace, \N is new line, and \T is horizontal tab. When they appear in printf format strings, these escape sequences represent actions to perform upon printing. Printing \A causes an audible beep on most machines. Printing \B moves the cursor back one position. Printing \N advances the cursor to the beginning of the next line. Printing \T moves the cursor to the next tab stop. A string may contain any number of escape sequences. Consider the following printf example, in which the format string contains 6 escape sequences. Printf, quote, item, tab, unit, tab, purchase, \n, tab, price, tab, date, \n. Executing this statement prints a 2-line heading: item, unit, purchase, price, date. Another common escape sequence is \quote. Using the quote character, double quote, since the double quote character marks the beginning and end of a string, it can't appear within a string without the use of this escape sequence. Here's an example. Printf, quote, \quote, hello, \quote, quote. The statement produces the following output, where you print literally, quote, hello. Incidentally, you can't put a single \ character in a string. The compiler will assume that it's the beginning of an escape sequence. To print a single \ character, put 2 \ characters in the string. You have to escape the escape. Cool. That was 3.1. So let's go back up here. Hey Tim, how's it going? Make a drum machine with print A commands. Just a bunch of tabs and just like You could probably make like maybe Morse code or something if you got like a long beep and a short beep. You could type out Morse code. I don't know. Let's go back up and finish our notes. Thanks for coming in, Tim and Jimmy, today. You guys were our first chatters so far. We've been streaming for 25 minutes. 28 minutes, actually. Kind of crazy, huh? Okay, so let's just get some stuff down here. Printf a function designed to display the contents of a string known as the format string with values possibly inserted at specified points in the string. When it's called, printf must be supplied with the format string followed by any values that are inserted. Okay, cool. So we'll go like this. Example, printf to string expression 1, expression 2, ... The format string can contain both ordinary characters, conversion specifications. Okay, so we have conversion specifications a placeholder representing a value to be filled in during printing. The information that follows the percent character specifies the value, how the value is converted. Begins with percent and is followed by a character, either like F, E, F, G, E, etc. That specifies how the value is converted from its internal form, binary, to printed form, characters. So for example, print F to whole number percent D backslash N quote I. Okay. Where I is an integer and is inserted at percent %d within the string yeah. Where is the C project? We're getting there. We're getting there. We gotta get our basics first. Then we gotta figure out what we want to do. Okay, cool. Integer specifier within integer conversion. Okay, cool. So yeah, we know that. Just print stuff out. Cool. So you know you can't if you have more specifiers than variables, you get garbage values, and then you abstract out values if you don't have enough. So we'll say note C compilers or the compiler does not specify aren't required C compilers aren't required to check the number of conversions in the format to match the number of output items. Okay. Cool. Conversion specifications, we already did that. A great deal of control, we'll talk about it. Okay, cool. So, so I'm going to do an example here, or do another note here for this, and say additional formatting, optional formatting, right? You can do this, %m dot p x, or percent negative m dot p x, quote. So this says m is the M is the number of characters, the minimum field of characters. The minimum field width, right? The minimum number of characters to be printed within, to be reserved for that variable or insertion, value insertion, right? Then you have percent dot p, right? The dot p is the number of required characters, either rounded or created in the conversion specification. Optional. The value to be printed required and character value, right? Precision isn't easily described on the conversion. Okay, so this is the precision, either like rounding or added values for required length of actual value, right? So a positive m indicates left, no, right bound characters, or right justified characters, or yeah, negative m indicates left justified characters. Precision of inserted value. So I'm going to give another example here. Actually, I'm going to print out I'm going to take example here. Copy image. Like that. And then I'm going to add in a copy of the output. Put that there. Nice. Cool. I like that. Hey Ray, how's it going? Welcome back in, my dude. Appreciate you being able to join me tonight. Okay, cool. So let's just jot down these specifiers really quickly. So most common conversion specifiers are common conversion specifiers. One is going to be D, which displays an integer in decimal base 10 form. P indicates the minimum number of digits to be displayed. Extra zeros are added to the beginning of the number if necessary. If P is omitted, it's assumed to have the value of 1. In other words, it's the same as for 0.1. Cool. 2, E displays a floating point number in exponential format, scientific notation. P indicates how many digits should appear after the decimal point. The default is 6. If P is 0, the decimal point is not displayed. Okay. Number 3, F. So F displays a floating point number in fixed decimal format without an exponent. P has the same meaning as for E. Number 4, G displays a floating point number in either exponential format or fixed decimal format, depending on the number's size. P indicates the maximum number of significant digits not after the decimal point to be displayed. Unlike the F conversion, the G conversion won't show. Oh my gosh, come on. Trailing zeros. Oh. Yeah, won't show trailing zeros. Furthermore, the value we print has no digits after the decimal point. G doesn't display the decimal point. Cool. So these are just a few. So we'll say few common conversion specifiers. We'll say common. Whatever. Hey, what's up, Syed? Appreciate you for joining me again. Welcome back in. Welcome, welcome, welcome. Okay, we got that example down. We got that. Cool. All right, let's talk about some escape sequences really quickly, and then that'll wrap up this section. We can move on and wrap up the chapter. Escape sequences. Right? The escape sequences enable strings to contain characters that would otherwise cause problems for the compiler, including non-printing control characters and characters that have special meanings to the compiler, such as double quote. Nose is itchy. Including non-printing control characters such as double quote. So here's some common escape number 1, \A. Okay, I cannot type today, dude. Number 2 is going to be \B. 3 \N. 4 \T. Okay. \A is alert bell. Backspace. This is new line. This is horizontal tab. Move it back one position. So this is cursor moves back one position. Audible beep. So this is like alert. This is like an audible beep. Right, new line. Move cursor to begin next line. Pretty tab moves cursor to the next tab stop. Cool. Nice. And then you can escape the quotes as well. So we'll say to escape quotes, literal, to print literal quotes. Or backslashes, escape them using, so this would be like here, example, backslash, quote, like normal. Okay, cool. That handles that. So now I think we're good to move on to section 3.2. The scanf function. Okay, so the scanf function. There we go. Let's jump into section 3.2, the scanf function. Just as printf prints output in a specified format, scanf reads input according to a particular format. A scanf format string, like printf format string, may contain both ordinary characters and conversion specifications. The conversion specifications allowed with scanf are essentially the same as those used with printf. In many cases, a scanf format string will contain only conversion specifications, as in the following example, where we have int I and j and float x, y. We scanf %d, %d, %f, ampersand I, ampersand j, ampersand x, ampersand y. Suppose that the user enters the following input line: 1, negative 20, 0.3, negative 4.0 E3. Scanf will read the line, converting its characters to the numbers they represent, and then assign 1, negative 20, 0.3, and negative 4000.0 to I, j, and x, and y respectively. Tightly packed formatting strings like %d, %d, %f are common in scanf calls. Printf format strings are less likely to have adjacent conversion specifications. Scanf, like printf, contains several traps for the unwary. When using scanf, the programmer must check that the number of conversion specifications matches the number of input variables that each conversion is appropriate for, the corresponding variable. When using scanf, the programmer must check that the number of conversion specifications matches the number of input variables and that each conversion is appropriate for the corresponding variable. As with printf, the compiler isn't required to check for a possible mismatch. Another trap involves the ampersand symbol, which normally precedes each variable in a scanf call. The ampersand is usually but not always required, and it's the programmer's responsibility to remember to use it. Forgetting to put the ampersand symbol in front of a variable in a call to scanf will have unpredictable and possibly disastrous results. A program crash is a common outcome. At the very least, the value that is read from the input won't be stored in the variable. Instead, the variable will retain its old value, which may be meaningless if the variable wasn't given an initial value. Omitting the ampersand is an extremely common error. Be careful. Some compilers can spot this error and produce a warning message such as forgot argument is not a such as some compilers can spot this error and produce a warning message such as format argument is not a pointer. The term pointer is defined in chapter 11. The ampersand symbol is used to create a pointer to a variable. If you get a warning, check for a missing ampersand. Calling scanf is a powerful but unforgiving way to read data. Many professional C programmers avoid scanf, instead reading all data in character form and converting it to numeric form later. We'll use scanf quite a bit, especially in the early chapters in this book, because it provides a simple way to read numbers. Be aware, however, that many of our programs won't behave properly if the user enters unexpected input. As we'll see later, it's possible to have a program test whether scanf successfully reads the requested data and attempt to recover if it didn't. Such tests are impractical for the programmers in this book. Such tests are impractical for the programs in this book, but they would Such tests are impractical for the programs in this book. They would add too many statements and obscure the point of the examples. It's just saying, like, scanf, right? You have to just be wary of user input in scanf, because if the user enters input that's incorrect to the format you're specifically looking for, you can get some weird things happening. But it's not going, and so you can write some code to make sure, like, to do checks on the user input, but they're not really going to show them in the examples because it's just not really necessary for the gist of what they're trying to show. It's kind of more of proper programming behavior, checking input and stuff that's good to know. But for what it's teaching, it's like going to abstract that out. How scanf works. Scanf can actually do more than I indicated so far. It is essentially a pattern matching function that tries to match up groups of input characters with conversion specifications. Like the printf function, scanf is controlled by the format string. When it is called, scanf begins processing the format. When it's called, scanf begins processing the information in the string, starting at the left. For each conversion specification in the format string, scanf tries to locate an item of the appropriate type in the input data, skipping blank space if necessary. Scanf then reads the item, stopping when it encounters a character that can't possibly belong to the item. If the item was read successfully, scanf continues processing the rest of the format string. If any item is not read successfully, scanf returns immediately without looking at the rest of the format string or the remaining output or the remaining input data. As it searches for the beginning, I cannot read today, you guys. As it searches for the beginning of a number, scanf ignores white space characters. The space horizontal and vertical. Oh gosh, I'm sorry, you guys. The lines are getting crossed up. The words. Okay. As it searches for the beginning of a number, scanf ignores white space characters, the space, horizontal and vertical tab, form feed, and new line characters. As a result, numbers can be put on a single line or spread out over several lines. Consider the following call to scanf. Scanf %d %d %f %f for I, j, x, and y, all with ampersands. Suppose that the user enters 3 lines of input. 1, new line, -20 spaces, 0.3, new line spaces, -4.0 E3. Scanf sees one continuous stream of characters. I'm using the dot to represent the space character and this to represent the new line character. Since it skips over white space characters as it looks for the beginning of each number, scanf will be able to read the numbers successfully. In the following diagram, an S under a character indicates that it was skipped, or an R indicates it was read as part of an input item. Scanf peeks at the final new line character without actually reading it. This new line will be the first character read by the next call of scanf. What rules does scanf follow to recognize an integer or a floating point number? When asked to read an integer, scanf first searches for a digit, a plus sign, or a minus sign. It then reads digit until it reaches a non-digit. When asked to read a floating point number, scanf looks for a plus or minus sign, optionally followed by a series of digits possibly containing a decimal point, followed by an exponential optional, an exponent optional. An exponent consists of the letter E or capital E, an optional sign, and one or more digits. The %E, F, and G conversions are interchangeable when used with scanf. All three follow the same rules for recognizing a floating point number. When scanf encounters a character that can't be part of the current item, the character is put back to be read again during the scanning of the next input item or during the next call of scanf. Consider the following admittedly pathological arrangement of our four numbers. 1, negative 20.3, negative 4.0, E3. Let's use the same call of scanf as before. Here's how scanf would process the new input. Conversion specification %D, the first non-blank input character is 1. Since integers can begin with 1, scanf reads the next character, negative, minus sign. Recognize that minus signs can't appear inside an integer. Scanf stores 1 into I and puts the character back. Conversion specification %D, scanf then reads the character negative, 2, 0, and the period. Since an integer can't contain a decimal point, scanf stores negative 2, 0 into J and puts the period character back. Conversion specification %F, scanf reads the characters, the decimal point, then the 3, and the negative sign. Since a floating point number can't contain a minus sign after a digit, scanf stores 0.3 into X and puts the negative character back. Conversion specification %F. Lastly, scanf reads the character negative and 4 and period and 0, E, 3, and the new line symbol. Since a floating point number can't contain a new line character, scanf stores this into Y and puts the new line character back. In this example, scanf was able to match every conversion specification in the format string with an input item. Since the new line character wasn't read, it will be left for the next scanf call. Cool. Yeah, Blastoderm, that's probably a good practice, right? Just use %S with scanf and convert the string to a specified type later, right? Always take in just kind of treat it like a Python input function, right? That's probably a good practice. All right, a couple more pages, then we're done with the chapter. I think 2 more. Ordinary characters in format strings. The concept of pattern matching can be taken one step further by writing format strings that contain ordinary characters in addition to conversion specifications. The action that scanf takes when it processes an ordinary character in a format string depends on whether or not it's a whitespace character. Whitespace characters. When it encounters one or more consecutive whitespace characters in a format string, scanf repeatedly reads whitespace characters from the input until it reaches a non-whitespace character, which is put back. The number of whitespace characters in the format string is irrelevant. One whitespace character in the format string will match any number of whitespace characters in the input. Incidentally, putting a whitespace character in a format string doesn't force the input to contain whitespace characters. A whitespace character in a format string matches any number of whitespace characters in the input, including none. Other characters. When it encounters a non-whitespace character in a format string, scanf compares it with the next input character of the two-character match. When it encounters a non-white space character in a format string, scanf compares it with the next input character. If the two characters match, scanf discards the input character and continues processing the format string. If the character doesn't match, scanf puts the offending character back into the input, then aborts without further processing the format string or reading characters from the input. For example, suppose that the format string is %d %d divided by %d. If the input is space 5 back, oh my gosh, dude, I cannot talk today. If the input is space 5 / space 96, scanf skips the first space while looking for an integer, matches %d with 5, matches the / with the / and skips a space while looking for another integer and matches %d with 96. On the other hand, if the input is space 5 space / space 96, scanf skips one space, matches %d with 5, then attempts to match the / in the format string with a space in the input. There's no match, so scanf puts the space back. The space / space 96 characters remain to be read by the next call of scanf to allow spaces after the first number. We should use the format string %d space / %d instead. %d space / %d instead. Confusing printf with scanf. Although calls of scanf and printf may appear similar, there are significant differences between the two functions. Ignoring these differences can be hazardous to the health of your program. One common mistake is to put ampersand in front of variables in a call to printf. Fortunately, this mistake is fairly easy to spot. Printf will display a couple of odd-looking numbers instead of the values I and j. Since scanf normally skips whitespace characters when looking for data items, there's often no need for a format string to include characters other than conversion specifications. Incorrectly assuming that scanf format strings could resemble printf format strings. Incorrectly assuming that scanf format strings should resemble printf format strings, another common error, may cause scanf to behave in unexpected ways. Let's see what happens when the following call of scanf is executed. Scanf Haha, thank you so much for the follow, Azir. Appreciate you so much. Thank you so much. Appreciate you for that follow on Twitch. You're awesome. Thank you. If you guys are not subscribed to the channel or following, please do so. I appreciate you guys being here. Okay, let's go back here. Fortunately, this mistake is fairly easy to spot. Printf will display a couple of odd-looking numbers instead of the values of I and j. Since scanf normally skips whitespace characters when looking for data items, there's often no need for a format string to include characters other than conversion specifications. Incorrectly assuming that scanf format strings should resemble printf format strings, another common error may cause scanf to behave in unexpected ways. Let's see what happens when the following call of scanf is executed. Scanf %d, space %d, %i, %j. Scanf will first look for an integer in the input, which it stores in the variable I. Scanf will then try to match a comma with the next input character. If the next input character is a space, not a comma, scanf will terminate without reading a value for j. Although printf format strings often end with \n, putting a new line character at the end of a scanf format string is usually a bad idea. To scanf a new line character in a format string is equivalent to a space. Both cause scanf to advance to the next non-white space character. For example, if the format string is %d \n, the scanf will skip white space, read an integer, then skip to the next non-white space character. A format string like this can cause an interactive program to hang until the user enters a non-blank character. Adding fractions. This is a program. To illustrate scanf's ability to match patterns, consider the problem of reading a fraction entered by the user. Fractions are customarily written in the form numerator over denominator. Instead of having the user enter the numerator and denominator of a fraction as separate integer, scanf makes it possible to read the entire fraction. The following program, which adds two fractions, illustrates this technique. Adds two fractions includes standard io.h for our directive with our header file that we're importing. We have a main function that returns an integer and has no parameters. We declare some integer variables such as num1, denom1, num2, denom2, result num, and result denom. We say printf, enter first fraction space, and we call scanf to have the user enter a %d /%d, or integer over an integer in a fraction format. We're going to save this to number1 and denom1, or numerator 1. We're going to then ask for a second fraction and call this. And then we have result is equal to num1 times denom2 plus num2 times denom1. And the resulting denom is the denom1 times the denom2. The sum is %d /%d \n result num result denom, and return. A session with this program might have the following appearance. First, enter the first fraction, 5/6. Enter the second fraction, 3/4. The sum is 38/24. Note that the resulting fraction isn't reduced to lowest terms, right? There's no reducing happening going on here. Cool. And now we're on to Q&A. How's it going? Josh asks, he says, hello, do you ever feel going too broad instead of deep? Do you ever feel you're going too broad instead of deep? Do you think you'll learn more from starting up C than continuing your other languages? I don't know. I think I'm, I don't know. I'm not learning other languages in terms of going broad. I am going deep, pause, by learning C here in terms of I'm going to start writing some programs and maybe get like an Arduino or microcontrollers to start messing around with writing C programs, on like hardware level type of things and go deeper on that avenue. And then just go deeper in terms of using C to increase my knowledge in Python. I'm not going to stop writing code in Python just because Python is the most popular language in the world, right? It has tons of support and packages, and as the most, I don't know if it's the most popular, but I think it's the most used. I don't even know. I thought it was. It's one of those statistics. And yeah, so just knowing C, which, we can write programs in C and then convert those to Python or load those into Python for faster Python scripts if we wanted to too. So just knowing C is going to make us just an overall better Python programmer, and a programmer in general. So I think people need to bite the bullet and learn these lower things, and here we're learning them together. So thanks for coming in. Hey, Odin's son. I think people often get confused. They're like, oh, if you're like I don't know, like you can learn a lot of these topics like play off one another. Like this printf is just a function. Like you're just learning about a function as if I was reading documentation on a module or whatever. It's no different. I'm just like pretty much reading documentation here, learning a module or a language, a C programming language. So it's really no different than that kind of same thing I've been doing, but it just has a more, or I don't even know what I'm saying. Okay, Q&A. Question. I've seen the %i conversion used to read and write integers. What's the difference between %i and %d? Answer. In a printf format string, there's no difference between the two. In a scanf format string, however, %d can only match an integer written in decimal base 10 form, while %i can match an integer expressed in octal base 8, decimal or hexadecimal base 16. If an input number has a 0 prefix, as in 056, %I treats it as an octal number if it has a 0x or 0x prefix, as in 0x56. %I treats it as a hex number. Using %I instead of %D to read a number can have surprising results if the user should accidentally put 0 at the beginning of the number. Because of this trap, I recommend sticking with %D. If printf treats % as the beginning of a conversion specification, how can I print the % character? If printf encounters 2 consecutive % characters in a format string, it prints a single character, % character. For example, the statement printf net profit %d %%n profit might print net profit 10%. Oh, it says might print because we don't know the variable of 10 or of profit, right? It's like, why would you say might print? We know it's going to print that, but we don't know what the 10 variable is actually, profit is, instantiated as. What value is inside profit by this statement. The \t escape is supposed to cause printf to advance to the next tab stop. How do I know how far apart tab stops are? You don't. The effect of printing \t isn't defined in C. It depends on what your operating system does. When asked to print a tab character, tab stops are typically 8 characters apart, but C makes no guarantee. What does scanf do if asked to read a number but the user enters a numeric input? What does scanf do if asked to read a number but the user enters non-numeric input? Let's look at the following example. Printf enter a number, scanf %d and %I. Suppose that the user enters a valid number followed by non-numeric characters. Enter a number 23 foo. In this case, scanf reads 23 and storing 23 in I. The remaining characters foo are left to be read by the next call of scanf or some other input function. On the other hand, suppose that the input is invalid from the beginning. Enter number foo. In this case, the value of I is undefined and foo is left for the next scanf. What can we do about this sad state of affairs? Later, we'll see how to test whether a scanf had succeeded. If the call fails, we can have the program either terminate or try to recover, perhaps by discarding the offending input and asking the user to try again. Ways to discard bad input are discussed in Q&A section at the end of chapter 22. Question. I don't understand how scanf can put back a character and then read them again later. As it turns out, programs don't read user input as it's typed. Instead, input is stored in a hidden buffer to which scanf has access. It's easy for scanf to put characters back into the buffer for subsequent reading. Chapter 22 discusses input buffer in more detail. What does scanf do if the user puts punctuation marks, commas, for example, between numbers? Let's look at the first example. Let's look at a simple example. Suppose that we try to read a pair of integers using scanf. Enter 2 numbers, %d, and we'll save them in I and j. If the user enters 4, 28, scanf will read the 4 and store it in I. As it searches for the beginning of the second number, scanf encounters the comma. Since numbers can't begin with a comma, scanf returns immediately. The comma and the second number are left for the next call of scanf. Of course, we can easily solve this problem by adding a comma to the format string if we are sure that the numbers will always be separated by a comma, right? We can add that comma in there. And now we're on to the exercises and programming projects. So it looks like there's 6 exercises and 6 programming projects that we'll complete in our next session of this book. Cool. Let me do a little outro here for the recording. Or let me actually go through and take some notes on scanf here. Okay, so let's just do a note here, scanf. Just as printf prints output, scanf reads input according to a particular format. According to a particular format. A scanf format string, like printf format strings, may contain both ordinary characters and conversion specifications. Cool. Got you. Tightly packed strings are common. Okay, so I'll say, I'm going to take this example. Okay. put it down here. And then, nice. And I want to make a note here and say, forgetting to put the ampersand in front of a symbol will have unpredictable, probably disastrous results. Calling scanf is a powerful. So we'll get more into the pointer stuff later. It doesn't really give a lot of detail on it, so I'm not going to take notes because it really just says to like just use it, trust it for now. We'll get into pointers later. We know what pointers are based on our experience in CS50, but we're going to get some more solidification on them in later chapters. Calling scanf is a powerful but unforgiving way to read data. Nice. Okay, how it works. Here we go. Scanf actually does more than I've indicated so far. It's like pattern matching. For each conversion specification in the format string, scanf tries to locate an item for the appropriate type of in the input data, skipping blank space if necessary. So here, locate an item in appropriate type, blank space if necessary. Scanf then reads the item, stopping when it encounters characters that can't possibly belong to the item. As it searches for the beginning of a number, scanf ignores white space characters. Let's do a line. So we'll say ignores the white space characters. Right, these characters, nice. Cool. Using to represent that it skips those characters. Cool. What rule does scanf follow to recognize integer or floating point number? Okay, so we'll say rules scanf follows. When asked to read a floating point number, scanf looks for this. For a digit plus or minus sign and reads it. Okay, I'm just going to take this here. Conversion or interchangeable using scanf. Read digits, reading a floating point number, scanf looks for an exponent. Okay. Letter E or E. Scanf first searches for a digit plus a plus sign or minus sign, then reads it until it's non-digit. When asked for a read a floating point, so we'll say floating point scanf looks for say float. We'll say int here. We'll first search. The first search is for a digit, a plus sign or a minus sign. It then reads digits until it reaches a non-digit. For a float, looks for a plus or minus sign optionally followed by a series of digits, possibly containing a decimal point, followed by an exponent optional. An exponent consists of these here. Nice. No, not the viewers, not the bot. The bots! No. Archimedes, is it? Hey, it's the self-made. I wish, dude. Brilliant era. I like that. Brilliant. I like that's cool. I like that little pun. Thanks for coming in, dude. Hey, Mang, how's it going? What's going on, little bro? Big bro. Am I like ung status now? So much aura? Bro, come on. All right. Um, right, we already talked about that it uses a buffer. Um, so any kind of so put back. Okay. So it skips over not white space characters, but can take in ordinary characters to match to a pattern of with ordinary characters, like you would match like a regular expression string almost, but with these type of indications for the expressions, right? Okay. So I'm going to. Okay, that's fine. Anything here we want to add to our notes? Confusing with printf? No, print is so no, we don't need to do that. That's kind of just like, duh. Don't add those. Here's an adding fractions example. Okay, I guess I'll just take this example code and put it in here because it'll be good to have. I'll go like this. Take this guy, copy image, this here, and then we'll put the next one right below it. Let me actually delete this. Which one is this one? Image 4. Delete this. Let me actually get a little bit more space here. So it's a little bit more zoomed out. There we go. So now that's better. Here we go. All right, cool. Now we're on the Q&A. Asked AI whether scanf returns anything. It returns an int representing the number of successful reads. Oh, that's cool. That's a good thing to put here. Let's write that in. That's actually a really good thing. So we'll say returns an int representing the number of successful reads. Is successful one L or two L's? I think it's just one. I always get that. Successful reads. That's a good note. I like that. Clutch, clutch, clutch. Returns an integer. Oh, we'll do this. Let's say integer. Representing. Cool. So this was our notes we got today. So let's go ahead and take a little review over what we learned about today. So in chapter 3 was all about formatted input-output. We have the printf function, which is a function designed to help display the contents of a string known as a formatted string. with values to be inserted into it, or various expressions. These expressions or these values to be inserted are represented via these conversion specifications, and these have various kind of flags associated to the type that this variable or value is going to be inserted into the string. We have some optional formatting to these specific flags for specifying, rounding or maximum amount of characters, reserved character, like a reserved character spacing with a maximum amount of precision characters within that. Cool. And then we got some examples. We also learned that with that kind of indication that you can have left or right justified characters within that buffer of fully that field of characters indicated by the M value, right? The minimum field, which is basically like, okay, no matter what, I have a minimum field of 5 character spaces. If my number is 3 character spaces, it doesn't matter. I add 2 extra characters of blank white space at the end. I'm just reserving a set amount of characters for this input, and then I can format a precision of that input within it. Think of it like almost like a buffer of character space. Right? We also note that the C compilers aren't required to make sure that the number of conversion specifications matches the number that are in the format string, right, of outputs of like variables to be converted into. So you have to make sure you match them up accordingly as a programmer. And then there's some common escape sequences we learned about that we've kind of known about: alerting, backspace, new tab, or new line and tab, and escaping quotes and literal backslashes as well. We then moved on to 3.2, which was all about scanf. Very similar to kind of like input function in Python, but this is obviously, it doesn't always return a string. This returns various types of values to you to kind of save and receive from user input via the terminal. And you have to specify those values by saving them via their pointer with the ampersand in front of them. Now, there are pitfalls with scanf, as it's very specific to how users input the data, and you need to be careful to make sure that users are inputting the data correctly and in the right formats, because if they don't, things can break. And so you never really want to rely on user input solely. So like we said and we discussed earlier, the right way to probably go about it is just converting it taking in everything as a string and then doing conversions on individual elements yourself. Cool. The integer. So this is how scanf looks for items, right? It parses through kind of how it does like expressions and as you would think, what it detects for to kind of make up integers and floats and what it looks for in those values. All right, you guys, that was chapter 3, formatted input output. I really hope you enjoyed that. I'm going to stop the recording here. Thanks so much for being here, and I'll see you later in the next chapter. All right, that was the end of the recording. I'm not stopping the stream yet, guys. Don't have to pass out yet. Hold on. That was just the recording. Cool. If you guys enjoyed that chapter 3 read along, please leave a like on the stream. It does actually take a lot of effort to read out loud for an hour and a half straight. It is pretty taxing, like my voice, and I'm not trying to be like begging for the likes. No. But I appreciate you guys being here and hanging out with me as we read chapter 3 today. This was really informative. Honestly, like I didn't think I was going to learn a lot about this in this chapter. I thought it was going to be pretty a lot of review. Right? I thought it would be the end of more review, but I learned a lot actually about how these functions work under the hood regarding detecting the white space skipping in the scanf, as well as some other things as well, like the precision in printf, how you can have precision in M. I didn't really fully understand the M and P in the optional formatting for printf functions, and now it really kind of solidified that and brought it home for me. So really good that we were able to wrap that up and get that going here. So if you guys enjoyed chapter 3, smash a like here. Sorry about all my my jumbles and my what is it called? Cat got my tongue. Scanf can also return -1 or 0 as failure. So its success as an int is greater than 0. or negative one. Okay, so um, successful reads or 0 and 0 or negative 1 for failure. Okay, cool. If we do not pass a pointer, dump-C compilers can interpret the past variable's value as memory address. If we don't pass a pointer, dump-C compilers can interpret the past variable's value as a memory address. Right, because we have to actually go to that. Right, you're saving at this memory location a value with the ampersands, right? Right, with the ampersands, you're saving the value entered at this memory address, and then instantiated, encompassed by this variable j, which is defined, elsewhere, that you can access again. Now, if we wanted to dereference the value and actually print it, we would do what? Star j. Like if we print star j. Now, we haven't had to talk about this yet, but we've been declaring these variables, and we only really had to talk about the free function when we started to talk about like arrays. But we don't have to free variable memory. Is variable memory just random access memory, meaning that it's just can be kind of picked up and disposed of, and we're not actually allocating? Or am I getting that wrong? Is an array also random access RAM, and you're just instantiating, reserving space, a designated space? Or maybe not, because that wouldn't, I don't know, that doesn't make sense. Because you don't have to free variables, because it seems like variables are kind of just like saved in a place in memory that can be just constantly overwritten and reused and picked up and put down and kind of reference and dereference rather quickly. But maybe we have to set up some different type of memory. This is the kind of stuff I want to learn about. It's very intriguing how they all works together. I mean, if we don't use ampersand for a non-pointer variable for scanf, old C compilers might interpret the value stored as if it were an actual memory address. Okay, yeah. Local variables are created on the stack region. Yeah. Local variables are on the stack, which is the yes, the stack is located in RAM. It's a specific area in RAM used to store temporary data during program execution, such as local variables, return address, and function parameters. Okay, cool. So you don't have to free stack memory? Question mark? Yes, you do not have to manually free memory allocated on the stack. Memory on the stack is automatically managed and is automatically discarded when the function that allocated is returns. This automatic cleanup occurs because the stack appears in last in, first out data structure, where variables are pushed onto the stack when the function is called and popped off when the function exits. As a result, stack variables are local to the function and cease to exist. Exactly, okay, perfect. So this is really helping, like exactly how, like in Python on function stack calls and stuff like that. Once the function completes, eliminating the need for explicit deallocation. This automatic management is a key advantage of stack allocation, making it faster and less error prone than heap allocation. Okay, so when we want to assign a area, so the heap is used to reserve space for like arrays, question mark? Yes, the heap is commonly used to reserve space for arrays, especially when the array size is not known at compile time, needs to persist beyond the lifetime of a function, or is too large to fit on the stack. In language like Java, arrays are treated as objects and are always located on the heap, allowing them to outlive the function that created them and be accessed from multiple parts of the program. This is crucial because stack memory has a limited size and is automatically managed, making it unsuitable for large or long-lived data structures. Heap allocation also enables dynamic resizing and prevents stack overflow errors that could occur with large stack allocated arrays. Okay, now we're getting into this stuff. This is what we want to know. Okay, I'm glad we're hitting this stuff again because it's becoming easier the second or third time around and hearing it again, right? Okay, so let's talk about the stack and the heap. I am learning about C and I'm wanting to understand them better. And I'm not exactly into memory management and allocation yet within my book. I'm more at the beginning, but I'm learning about scanf right now and the preceding ampersand that comes before the variable that you wish to receive the the input from. So this ampersand, from my interpretation, is referencing the memory address at which we are wanting to save the input value or data point that the user is entering. And if we want to then access that, it is going onto the stack for quick access, which is located within the random access memory of the computer. And this memory is last in, first out, meaning that things are stacked up on top of each other and variables that aren't used anymore locally are discarded. But if we have large data that we want to save for the lifetime of the program and to access from globally, or just memory within the computer we want to reserve, we would allocate that onto the heap data. What is it, a data structure or whatnot? I'm not sure. Now this would now I'm trying to understand, I guess, the heap a little bit better because it kind of seems a little abstract. And then there's obviously like this balancing act that happens between them, um, to within is it the total memory of the computer, or let's have what is this? Let's talk about it.
You're on the right track. The stack and the heap are indeed two different areas of memory with different purposes. The stack is where all your local variables and function calls live. It's super fast and follows a last in, first out order, which means that when a function is called, its variables are pushed onto the stack, and when the function returns, they're popped off. This makes it very efficient, but
Okay.
also limited.
Sorry, keep going.
No worries. So the heap is a much larger pool of memory and is used for dynamic memory allocation. That means you can allocate and free memory as needed during the program's runtime. It's not as fast as the stack because it's and because the heap is managed manually in C, you have to be careful to allocate and pre-memory properly to avoid leaks or dangling pointers. But the advantage is that it allows for more flexible memory usage and can handle larger data structures that need to persist beyond the scope of a single function. So it's definitely a balance between the two.
Well, I often see this metaphor or like illustration that they are kind of like working in balance or in tandem with one another, pushing and pulling or giving and or whatnot. How does that work?
Yeah, that metaphor is pretty common. Essentially, the stack and the heap are like two different resources that your program uses. The stack is quick and efficient, but limited in size, while the heap is large and flexible, but a bit slower. When your program runs, it tries to balance these two. For example, local variables go on the stack, but if you need something that lasts longer or is too large, you allocate it on the heap. If you run out of stack space, get a stack overflow, and if you don't manage heap memory well, you get memory leaks. So it's definitely a balancing act between speed and capacity.
This might seem like a dumb question, but how do you know if you're going to approach a stack overflow? Like obviously if you call like recursive functions like so many times or is it kind of like hardware dependent or is there typically I know in Python they have right the actual baked in barrier to that you can modify and increase to prevent stack overflow or whatnot but in C and these lower level languages, how do you understand that? And then also for like allocating memory on the heap, how do you know that you have memory available within your computer? I know computers nowadays have more and more memory, but I'm assuming back in the day when things were much much smaller on these like those cryptic devices or ancient devices, that memory management was much more, like, I don't know, was it much more relevant, or I don't know.
Those are great questions. In C, the stack size is typically set by the operating system and is relatively limited. If you use too
Okay.
much stack space, for example, through deep recursion or large local arrays, you can cause a stack overflow. Some compilers and operating systems let you adjust the stack size, but it's generally a fixed limit. You can often get a sense of this by how large your function call stack is or by running into errors when the stack is exhausted. As
Okay.
for the heap, it's a bit different. The operating system manages the heap and it will allocate memory as long as there's free space. If you try to allocate more memory than is available, you'll get a failure, often returning a null pointer. Back in the
Null
day, with
pointer.
less memory, it was definitely more crucial to manage this carefully. Nowadays, computers have a lot more memory, so it's a bit easier, but the concepts remain the same.
Okay, so you return this null pointer then, I guess, right? That if you can't get any memory left, like, bro, I got no inches left. Pause. That was a terrible analogy. Well, literally, it's got no inches of memory left to give. Like, I can't give you more. Here's nothing back. It gives you a null pointer back. She sounds like my ex. She sounds so real. Yeah, dude. So if you guys don't know, like, haven't used this feature yet of ChatGPT, it's actually really, really helpful. Like, yes, the voice is a little cringe and can be annoying sometimes when it does its like natural pauses trying to mimic human voice, but like talking through your ideas and and having an actual conversation back and forth as if it was a peer, like a knowing peer or something, that's what I treat it as. Like, I bounce my ideas and my conversation, like when I'm trying to learn, like conceptually, like conversationally with it, and it really, like, mimics that like peer to peer conversation almost that you would have like with a TA, and learning that way. And like I find myself in traffic, like all, like talking to literally like the speakers in my car, because like having a conversation about my projects and my code or whatnot when I'm just sitting there thinking. Like today I was thinking about the convex hole algorithm, and I actually thought of a couple of ways I think that we could maybe try it, or at least try to implement it. That kind of, it might be a little bit unique. I put a picture in our Discord, and so it was. Let me know what you think about that idea. Also, I want to bounce there, guys. It's kind of hard to understand, but um, yeah. Okay, cool. That helped a lot. For back in the day, I got this. I had this hack back in high school before like a lot of people caught on to it. I don't know. I'm gonna say I'm ahead of the curve. I might have not been, but when I was in high school and in beginning of college, when I had to write essays, what I did was I just used Google Docs voice push to text when it first like came out. That was kind of when it was like first coming out, like push to talk, like voice recognition stuff was kind of first coming out in on the iPhone and on Android and stuff, and in Google Docs and whatnot. So I started to use that to just talk through my essay, and it really gave my essay like an actual like real world, real voice to it, because I wasn't like in my head typing out like a structured format. I was literally like giving like a speech and then having it transcribe my speech, and then I would go through and just edit and basically submit like a speech essay almost. And it really helped like with flow and all that as well. So like that was a hack I had back in the day. But now AI just writes it for you. Okay, cool. That was a lot of good information there. I feel we're definitely going to get into more memory stuff. We haven't even gotten into memory stuff yet, and we're already starting to ask those questions, which is really good. So, coming into the next stream, we'll bang out these exercises and practice programming projects. and it should be some good practice to actually get some more printf and scanf implementation here. So thank you guys so much for joining me and hanging out with me today. We streamed for an hour and 50 minutes as we had learning C, reading C Programming: A Modern Approach, second edition by K and King. I really appreciate everybody being here. Let me just actually quickly catch up on. We got a lot of chats from our boy Blasto here. Stack is discarded when a function returns. Malloc allocates on the heap region and requires exactly one free to deallocate it, and gets the memory of a variable no matter that is from the stack or the heap. Most variables are created on the stack, but using malloc, that variable is pointing to the heap region. Okay, so you can actually malloc on a variable as well. So if you want to save the variable, okay, let's ask that as well. So can you assign, I think I muted. Can you instantiate a variable on the heap as well, rather than on the stack if you actually deliberately call a malloc on it, if you want to keep it like globally, let's say?
Absolutely, you can. And see if you use functions like malloc, calloc, or realloc, you're allocating
Malloc.
memory on the heap. That means the variable or data structure you create will persist until you explicitly free it with the free function. This is really useful if you need that memory to last beyond the scope of a function or even the entire program. Just remember to keep track of it and free it when you're done to avoid memory leaks.
So, I mean, what's the difference then of just like having a variable defined like at the top of our program, like globally, and then using it within like a later function, like as if you would in Python, or
That's a
yeah, like is there any like difference or like I don't know.
There are definitely some differences. When you declare a global variable, it lives for the entire duration of your program, and it's accessible from any function. This is a bit like having a permanent variable that doesn't need to be allocated on the heap. However, global variable can make your code harder to manage because they can be changed from anywhere, which can lead to bugs that are tough to track down. On the other hand, when you allocate memory on the heap with malloc, you have more control over its lifetime. You can allocate and free it as needed, and it's not accessible globally unless you pass around pointers. This can make your code more
So
modular.
is that what Python is doing under the hood with your variables that are defined like globally outside the scopes of your functions?
In a way, yes. Python does handle memory management for you, so you don't have to worry about the stack and heap in the same way as in C. When you define a variable at the global scope in Python, it stays accessible throughout the program's lifetime. Python's memory management is more abstracted and it uses a garbage collector to clean up unused objects, so you don't have to manually free memory. It's definitely a different approach compared to C, but the underlying idea of having variables that persist is quite similar.
Hmm. Okay, interesting. We're gonna definitely get into some more memory stuff later in the book, which is gonna really be good for answering these questions. So it's good that we have these questions now, though. We're definitely interested. Hey, Root, how's it going? Best of luck to you. Thanks for coming in. All right, see you, everybody. Thanks for coming in, dude. We say what's returned by malloc to a variable. That variable will be a pointer to the heap region. Yeah, so the malloc returns, depending on what size or whatever we wanted, right? A chunk of memory on the heap, a location, and then we can go ahead and in that location add various things, right? All right, cool. I'm gonna head out here, you guys. This was a good discussion. We streamed for 2 hours today. Appreciate all the love and all the. If you guys could give a like on the stream, give it a little thumbs up and subscribe so I can see you tomorrow. My goal is, my goal is to hit 5K subs by the end of the year. My goal, that was my goal at the beginning of the year, was 5,000 by the end of 2025. So hopefully we can hit that. So thank you guys so much for being here. Blasto, Mang, Ray, Root, Huss, Zen, Tim, Archimedes, Odinson, Force of Nature, SSLO, Josh, Syad, Jimmy Boats, all y'all. Clutch, everybody, clutch. I gotta work now. Well, goodbye, big bro. Later, Meg. All right, see you guys tomorrow. Message me on Discord. Peace out.